Hi and good day. For this lecture we are going to take a look at the concept of asymptotes and in connection to infinite limits. We have taken a brief look at this thing before, and now we're just specializing on this topic. This is going to help us to understand the limits a little bit more and also get us ready for graphing of functions. Typically in Calculus 1 you come across three types of functions that have asymptotes and therefore have infinite limits. They fall in these three categories. There are the rational functions, rational function would be something like this, say 2x minus 3 over x minus say 5. That's an example of a rational function, a ratio of two polynomials. Type 2 to look at are trigonometric functions. This is as good of a time as any to go back and refresh your memories about trig functions, some of their properties. Some videos are posted related to them. But right now we're just looking at the very basic functions. For example, we might take a look at, say, tangent of x or cotangent of x or secant of x and such. These are examples of trig functions that have asymptotes. Type 3, we are going to look at logarithmic functions. Example would be y is equal to, say, logarithm of x minus 5 in base 2. Another example would be y is equal to natural log of, say, x minus 1. Okay, what is involved in any of these functions? They have the property that when x approaches a certain special value, the value of y goes to infinity or minus infinity. So as x approaches a special value, as this happens, y goes to either plus or minus infinity, or perhaps both of these things are going to occur on either side of the special value. Let's go ahead and take a look at this. So I'll go back to example of rational functions first. Here we brought up this example of 2x minus 3 over x minus 5 here. Y is equal to, say, 2x minus 3 over x minus 5. At what point do we have an infinite limit for this function? Well, for rational functions, infinite limits happen where the denominator becomes 0 while we check to make sure the numerator hasn't become 0. So if denominator becomes 0, but numerator is not 0, then the function is going to have an infinite limit and an asymptote. at the point where the denominator became 0. So, for example, when you are facing this function, you set the denominator equal to 0. That tells you that x minus 5 is set equal to 0. That in turn tells you x is equal to 5. You go and check the numerator. Numerator at this point becomes 2 times 5 minus 3 is 10 minus 3, that is 7. That is obviously not 0. So x at x equal to 5, the limit of this function, let me call this the function f of x. We can say that the limit of f of x as x approaches 5, well, first time around we can say it just doesn't exist. A little bit more specific than that is to say it's infinity. So first we say does not exist. Now if you want to specify this a little bit better, we go back and make a table for this. Here's x, here's y, which was 2x minus 3 over x minus 5. Our target point for x is 5. We want to come close to 5. We pick numbers on either side. For example, I could start at say 4 and 6 on either side. Then I start marching toward 5. We want to make a quick march. So for example, I come to 4.9 and 4.99 and so on. On this side, I can come to 5.1, 5.01 and so on. Let me make some room for it. Here 5.1, 5.01 and so on. This will be 4.99. So if you take 4 and plug it in this function, you get 2 times 4 is 8 minus 3, that's 5, divided by minus 1, that's going to be minus 5. Taking another step, 4.9, 2 times 4.9 minus 3 divided by 4.9 minus 5, that is 9.8 minus 3 over minus 0.1, 5.8 over minus 0.1, that is minus 58. Yeah, I got minus 58. You can try that one. You see it's even much larger negative number and so on. On the other side, you can plug 6, for example. 12 minus 3 is 9 over 1, so it starts at 9 here. At next step, 5.1, when you plug it, 2 times 5.1 minus 3 over 5.1 minus 5, that is 10.2 minus 3 over 0.1, 7.2.1, that is 72. I got 72 here. You can go ahead and find this value, find this value. That gives you the following a specific idea. As you come close to 5, from below, these numbers are marching toward minus infinity. So I write it like this. Limit of 2x minus 3 over x minus 5 as x comes close to 5 from below is minus infinity. On the other side, if you look at these numbers, you can conclude from them that the limit of 2x minus 3 as over x minus 5 as x comes close to 5 from above turns out to be plus infinity. So these numbers are headed to minus infinity. these numbers are headed to plus infinity. Sometimes to abbreviate this information, we employ a device like this. I draw a line here. This is the line indicating the asymptote. Really, at that point, at point 5, the function is undefined. On left of it, I write minus infinity. On the right of it, I write plus infinity, indicating just what I have discovered. On the left, I'm descending. On the right, I'm going up. That is exactly what happens on the picture, and that's what you use for graphing purposes. If that function is to be graphed, one principal component of the picture is it has lots of detail to this picture. We're just concentrating one item at a time. There's going to be a lot more things to say about this thing, really. 1, 2, 3, 4, 5. This is where the asymptote is going to be. So here's our asymptote. Call it a vertical asymptote. What we just discovered here is that from above to the right of 5, these numbers are marching all the way up to plus infinity. That tells me that my picture is going to behave like this. At left of 5, this is 5. At left of 5, we will have something that behaves like a function that goes to minus infinity, behaves like this. So we have piece of the puzzle. Here's like a bone for the function. Is a part of the skeleton of this function is this vertical asymptote here. It tells us where these tails exist, and so that's a major clue about the graph of this function. Rather major unforgivable mistake on the graphing of this function would be just to connect a point from here to a point there and assume that this function just connects from one point to another. Essential point of this function is that it is disconnected. There's a rupture in it, and that's one main feature to notice. Okay, whenever there is a vertical asymptote, one of 4 different generic pictures could happen. So 4 possibilities. If this is your vertical asymptote, as we just saw it, it could happen that on the left you're diving down, on the right you're going up. Other obvious possibility is just reverse of this, that on the left you are going up, on the right you're descending. It's also possible that on both sides you have the same behavior, that on both sides you're just pulling up to, say, plus infinity. Possibility number 4 is just you just descend on both. As you come close to the asymptote, you go down. What are the clues about the function that will tell you which one of them it's going to be? Really, the easiest thing to do is just to do point plotting, just like here. What we did, come very close to your asymptote. How close? Well, that depends on the function. You've got to be a bit careful on that. What's rather hard to go wrong with the basic kind of examples you see. Come very close, try it out. Carefully try it out. You will get information that's going to tell you what type of behavior to expect. So a surefire way of telling the difference between these 4 is just by testing. So keep in mind that you have a calculator. Any basic calculator these days can let you know what's going on. So find which one by testing. Well, if you want to advance the mathematics, you want to understand a little bit more as to, well, what happened that caused this kind of different type of behaviors. So this, let's write down the formula that we had. Like an example here was 2x minus 3 over x minus 5. What should I do to this function to make it flip upside down? Of course, an easy thing we can do is just multiply it by minus. So here an easy example for that is 3 minus 2x over x minus 5. I just multiply it by negative. It's going to make it flip over. Of more interest is that when would it happen that both sides will go up? Well, what we need to do is to control the sign that is created while this is going to 0. When x comes close to 5, if it is below 5 or larger than higher than 5, the sign changes. If you want to prevent the sign change, you have to, for example, square this or raise it to any even power. So here is an example: 1 over, or just about anything in the numerator, x minus 5 squared. So that squaring prevents the flipping of the sign. It pulls it up on both sides of the asymptote. If this power was 4, same thing will happen. 6, any even number would do. How could I create this? So minus 1 over x minus 5, for example, squared. So all of these things, all of these asymptotes are located at x equal to 5. And here are the pictures. Here I mentioned that even powers will create this kind of a situation. Here I should also mention that odd powers will create this situation. For example, if this was cubed, essentially picture looks like this, except that when the power goes up, the speed at which you are going to go to infinity also going to increase significantly. So here, if I had power 7, this will also look just like this, except that you are going to see a much faster progress toward infinity. So what's the shortcut to figure out for figuring out the type of behavior? You have to tell the difference between odd and even power in the denominator for the factor that is causing the vertical asymptote. So you factor your denominator, you look at the exponent, and from that you can tell, is it one of these two or is it one of those two? Well, between these, how do you figure out which one it is? Take the number in the denominator, which is location of the vertical asymptote, plug it in the numerator. Like here, x equal to 5 was the location of the asymptote. When you plug it in the numerator, here you get a positive number. You got 7. That goes with that positive number. Here, if you plug 5 in the numerator, you get minus 7. That's what you will have with a negative value. Same kind of story here. For example, if in the numerator here I had, say, x plus 2, picture will be essentially the same as this. How do I reason it out? X equal to 5 is the location of the vertical asymptote. Plug the 5 here. 5 plus 2 is a positive number. For positive numerator, that's the picture. For negative numerator, that's going to be the picture again. So you plug the quantity from the vertical asymptote in the numerator. From that, you can judge which one of the pictures is going to be. So here was the final verdict. If numerator is positive, that's how it's going to look like. Numerator negative. Here again, numerator positive. Here, numerator was negative. Where did we calculate numerator? At the location where the whole interesting thing is happening. between these two, exponent of denominator was odd. That happened to these two cases. Here the exponent of the denominator was even in these two pictures. Okay, that is so this discussion that I had here too, how do you figure out the shapes, is by analyzing two things. Is the exponent odd or even? Question number 2 is the value of numerator. At vertical asymptote, positive or negative, depending on what value the numerator takes, you get one of the 4 different possible pictures. Okay, that pretty much tells you the story of vertical asymptotes for rational functions. Next thing to take a look at is the story of trigonometric functions. So next topic is trig functions. Well, a main difficulty for students in calculus is that they have very little background in trigonometry. The courses offered in high school, they don't emphasize trigonometry enough, and that creates quite a bit of problem for students here, and especially at the beginning of calculus 2. So you'll be doing yourself a favor by going back to a trig book, a basic trig book, and try to bring yourself up to speed with respect to all various properties. And if there are areas there that you're not so sure of, try to spend some time on it and then come back here. So trigonometry deals with 6 functions, of course: sine, cosine, tangent, secant, cosecant, cotangent. They're just too numerous, and lots of relationships connect them to each other. So there is a whole truckload of facts and formulas there. Tend to be rather overwhelming unless you spend a long amount of time with them, and then it becomes second nature. Here, let's go take a look at some basic functions. You know that sine x looks something like this. This is an extremely quick review. Again, it doesn't substitute a text, it doesn't substitute taking a course in trigonometry. We're just quickly reviewing some of these items. Sine of x oscillated behavior like this. It goes indefinitely in both directions. There is no vertical asymptotes or anything like that. The function oscillates between 1 and -1. It crosses the x-axis at 0. If you are measuring in degrees, next place is going to be 180 degrees, next place is going to be 360 degrees, and so on. But in calculus, you need to use radian measure all the time. All of our formulas geared to that. So you need to switch gear a bit and be familiar with this fact that this is pi radians. This is really, let me write in a different color, 2 pi radians. This is minus pi, minus 2 pi, and so on. Okay, that was a quick look at sine. Now, if I want to take a look at y is equal to cosecant of x, who is cosecant? You remember that's 1 over sine of x. I'm taking the reciprocal of this function. What happens? Well, most of the time nothing significant happens, but if you divide by 0, you are going to get infinity, just like what we saw. So here is round 2 of this. Again, maybe I just go ahead and do my drawing here. When you divide by 0 and you are on the right of it, you are going to get infinity. So the function starts at infinity. Then it starts to descend. Reciprocal of 1 is 1. So that's going to be the bottom. So the function hits the bottom. Again, when the function comes, graph of function comes to close to 0, when the graph of the sine comes close to 0, cosecant is going to pull up to infinity again. So here is the graph of y is equal to cosecant of x. This blue one, of course, this was sine of x. So there is a vertical asymptote here. And y-axis itself is a vertical asymptote. Of course, you could try to memorize these things, but as I mentioned, after a while you'll see there is a truckload of these kind of information, and it's really impossible to memorize all of these things. You'll be forced to actually understand them. So once again, how would the graph of cosecant look like in the next half cycle? We expect at this 0, at any x-intercept of sine, we expect a vertical asymptote of a cosecant. Well, what does the graph look like? The graph, here the value of the function is close to 0 and negative. A reciprocal of it is going to be a large negative number. That means I'll be down here. Then what's going to happen? When you're all the way at the bottom, there's nowhere to go but to go up. What else is going to happen? Well, at this lowest point, at -1, reciprocal of -1 is still just -1. So I'll pull up all the way to here, and then as the value of the function goes towards 0, the reciprocal, the cosecant, is going to dive down all the way to -infinity again. And the story keeps repeating. These are periodic functions, so their behavior just keeps happening over and over again. I will have another piece of this type of tile up here, and same story on the negative side. Everything is very repetitive. It's going to be graph of this, or reciprocal of it. We're doing just everything by hand. That's how it's going to look like. So the short story is a vertical asymptotes at, let us write it down. You could say x, 0 itself was a possibility, next possibility 180, next possibility 360, next possibility here is going to be 540, and negative of all of these numbers. This is -180, minus 360, so really I have plus or minus in front of these. We said we try to push ourselves toward radian measures, 0, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so on. In short, I can represent all of these numbers as 180 times any integer. Integer means whole numbers, positive or negative. So 0, 1, 2, 3, -1, -2, -3. Typically we show them with n. So n is an integer. Here, same thing, n times pi, or pi times n if you wish. N, all right, n is an integer. We are going to repeat that phrase quite a bit. Integer, -3, -2, -1, 0. Those are your favorite numbers. 0, 1, 2, 3, 4, and so on. Keep going. Never stop. Makes integers. Okay. Next story that we could quickly mention is for cotangent of x. Who is cotangent of x? Cotangent of x is going to be cosine of x over sine of x. Well, you need to know a little bit about cosine, but without getting into too much detail here, numerator is not going to influence anything. We have the same function sine of x in the denominator that we had over there, and the vertical asymptotes going to happen at the same place that they happen here. Picture is going to be quite different, of course, but vertical asymptote at, so here's my abbreviation, vertical asymptote x is at n pi. Same story as before. To get a quick review about cosine and say something about secant and tangent as well, let's go take a quick look at that. Suppose I want to graph cosine of x. Quick review again. Here is what the cosine looks like. Good idea for you to stop this and graph it for yourself and come back and see if you are on the right track. Cosine, just like sine, oscillates between 1 and -1, and the difference is that it starts at 1 so something like this. So here is our height 1, here is the low point is -1. We have crossover points at 90 degrees, cosine of 90 is 0, this is 270, and so on. The next one is going to be at 450 if you wish. And the low point is at 180. Your high point again, of course, at 360. And negative, all of these numbers are going to show up on the other side. To represent it in radians, this is pi over 2. This is 3 pi over 2. This is 5 pi over 2. Okay. Cosine is uneventful. It's just a function with no vertical asymptotes, just nicely oscillating back and forth. A function that's going to be of more interest to us right now is a secant. That is just 1 over cosine of x. So we learn our lesson. Whenever cosine is 0, we are going to have vertical asymptotes for the secant. And here are where those things going to show up. So I'll have at pi over 2, cosine became 0, so secant is going to have a vertical asymptote. And then again at 3 pi over 2, story happens again. At 5 pi over 2, you will have it one more time. Minus pi over 2, of course, that's going to be another vertical asymptote. How does the picture look like? How do we quickly decide what's going on? Here we just talk it out. We don't really need a calculator. You go down here, the function is positive, cosine is positive. Reciprocal of that is going to be a positive but large number. Reciprocal of 0 is infinity, so the picture starts from all the way up here. Meets this function at 1, because the reciprocal of 1 is still 1. And then as this goes down, that one picks up speed and go back up again. So it looks like that. Do not confuse this with a parabola or any other function you have seen. It's really not anything else. It's just really secant of x, nobody else. Same story here. This is negative. Reciprocal of that is going to be negative infinity. You go up to -1. Reciprocal is just itself, and then you dive down again. And then one more round. Maybe I better use a different color up here so they don't run into each other. And and so on. So final statement to make here: vertical asymptotes at x is equal to, let's write it in friendly notation first, 90 degrees, 270, 450, and so on. Also happens at negative of these, so it's really plus or minus these numbers. How can I abbreviate all of these things with a formula? I can't say these are all multiples of 90. Well, they are all multiples of 90, but there are other multiples of 90 at which nothing happens. Like at 180, I don't have an asymptote. So this is not 90, 180, and so on. These are so-called odd multiples of 90. This is 3 times 90. This is 5 times 90, and so on. How can I capture odd numbers? Any number, I just write in. But how about odd numbers? Here's a simple trick that will do the job. Maybe you want to pause and come up with a formula yourself. Instead of n, what should I write? That only catches the odd numbers. So did you pause and come back? It's 2n plus 1. That is guaranteed to be odd. You multiplied by 90, and then you're all set. So the kind of numbers you see here are of this type: 2n plus 1, an odd number times 90. Once again, we remind ourselves, we try to go to radian notation. So it's plus or minus pi over 2, plus or minus 3 pi over 2, and so on. And the common formula for all of these here is more obvious. Is an odd number. Maybe I should have written that one too. That is plus or minus 5 pi over 2. So an odd number, 2n plus 1 times pi over 2. As we saw before, we expect same kind of a behavior for tangent. Y is equal to tangent of x. What's the definition of tangent? Do you remember that? That's sine of x over cosine of x. Once again, the item that is in the denominator is cosine, and they don't share zeros, so the vertical asymptotes of this one are going to be happening exactly at the same places that it happened for secant. Of course, the picture is going to be different. I invite you to draw that. So vertical asymptote for this, same as above. Okay, so that was a quick review of trig. You can apply what we learned about rational functions here as well. The issue is going to become a bit more complicated if you had like cosine of x, whole thing squared, or cosine square of x in the denominator. Try to figure out for yourself how the picture is going to look like for that, but I wouldn't take your time right now. I go to our third item that we promised today, which was what is going to happen for logarithmic functions. So item number 3 for discussion today was logarithmic. So we briefly went through this in class. You better go back and take a look at the section on logarithm, or better yet, go back to a text in pre-calculus or college algebra. Read through the section on logarithm, refresh your memory about what it was and what was supposed to do. Really, you're supposed to come to this course equipped totally for that. Otherwise, it's not really possible to start at that level and then go through all of calculus as well. That would be just too much. You have to take your time, make sure you have done the pre-calculus items, and then come to the calculus. Otherwise, it's just too much concept and too much formulas all at once. Logarithm, you remember we took a graph of, say, logarithm of x in base 2. Here's a quick review of that, what happened with this. Let's go ahead. We said if you don't have a calculator handy, you better choose some friendly numbers. And if you have your calculator, well, there is really nothing to worry about. What are the x's for which we can calculate the logarithm quickly and be done with it right now? At x equal to 1, I know logarithm of 1 is 0, logarithm of 2 in base 2 is 1, logarithm of 4 in base 2 is 2. So I skip 3. Well, I really need a calculator to know exactly what the value is, somewhere between 1 and 2, but I wouldn't know what. 8, logarithm of 8 in base 2 is 3, and so on. So here I'm doubling every time, and here it's increasing by 1 every time. What if I back up? Logarithm of 1/2 in base 2 is -1. Logarithm of a quarter in base 2 is -2. An eighth is -3. So on this side, as I go to infinity, this one also goes to infinity, but very, very slowly. Much more interesting is the following. On these numbers, as I back up, back down, back up, I don't know which one I should say, this is going towards 0. These numbers, as you go back, 1/2, quarter, an eighth, 16th, 1/32, and so on, you're marching towards 0. Where do these numbers go? Well, -1, -2, -3, and so on. They are all descending toward minus infinity. So in some sense, logarithm of 0 is minus infinity. Of course, your calculator typically says error if you really insist on taking logarithm of 0. What does all this mean on a picture? Let's go ahead and draw it and see what does it mean. Okay, that was the nicest straight line I drew in a whole year. Then suppose let me choose my x unit rather large, so I take this to be 1. So now I'm stuck with this. This will be 2, 3. We are skipping. We are reaching 4 here. Maybe I keep going. Well, I better stop, I guess. 4, say 5, 6. Chipping here a little bit. 7, 8. Here's my 8. So add 1, a value of the function is 0. At 2, it is 1. I have to go all the way to 8 to make it to 3. So you notice the snail-like behavior while it is going up. It's going up really slowly. On the other hand, when you go back down at 1/2, it's -1. It is 1/2. It's -1. I divide this by half. Now at the quarter, I have come down to -2. Then I go to an eighth. Again, they cut this by half, but here go down by an entire unit. See, these points are bunching up close to 0, and we are diving all the way down to minus infinity. This is going towards 0, and here we are going toward minus infinity. So we have a picture that looks kind of like this. So y is equal to logarithm of x in base 2. So moral of the story is that the vertical asymptote of this, where's the vertical asymptote? This is just the asymptote. This is a little bit different from what we had before. They shouldn't be touching really. They are just right close to each other. We don't have anything on this side at all. For logarithm, there is no picture here. So we just living on one side of this asymptote. We can still say vertical asymptote of it, the y-axis just at x equal to 0. That's the vertical asymptote. That is true for any of these basic logarithm function for logarithm of x in base b, vertical asymptote is this. If I take a logarithm of x in base 3, 4, or 5, any of them looks pretty much like this. If you take your base less than 1, I invite you to think about that, what's going to happen if you had, for example, logarithm of x in base 1/2. But that's a side point right now. Next issue is, here's a question. Where is a vertical asymptote of, say, y is equal to logarithm of x minus 3 in base 2. Remember, we had a short discussion about what happens if you replace the input of a function by a slightly modified input. Like, what happens if you use x minus 3 instead of just plain x? The effect is what? Pause for a moment and come back. What's the effect of? Here's the question. Like you remember from college algebra, the answer is graph of that function shifts right by 3 units. So if you subtract, it's going to go to right. If that puzzles you, go ahead and do it once by hand, entirely by hand, that function and the original, then you will see. If you try to divine it, not going to happen. Just go ahead and practice it, do it really, sweat over the topic, and then you will know why going to the right as opposed to left. So what's the answer to our question then? Remember, the graph we just drew looked like this. I will be drawing it quickly. This was logarithm of x itself. Here was 1, here 0. 2 important points. Now I'm moving to the right by 3 units. Everything is going to shift. So my 0 is going to come to 3, my 1 is going to come to 4. So my vertical asymptote is going to come here. My x-intercept, which was 1, is going to shift to 4. Picture is going to look kind of like this. So vertical asymptote is at x is equal to 3. Once again, your original asymptote just moved over. While the function moves, everybody moves alongside with it. Its x-intercepts moves, vertical asymptotes move. All the horizontal attributes of the function move by just exactly the same amount. Now all of this thing applies to the logarithm in base e as well. So if you take the logarithm in base e, that's how you write it. You remember that's same as logarithm of x in base e. And e itself, nothing mysterious, is 27.182 and so on. It's just a number, somewhere between 2 and 3. So picture is going to look just like the picture of logarithm of x in base 2 and so on. It's going to have vertical asymptote, just like that one. Vertical asymptote is at what? X equal to 0. So if I'd ask what's the vertical asymptote of logarithm of x minus 3, story will be same as that one. If you had y is equal to natural log of x minus 3, vertical asymptote is at x is equal to 3. So as simple as that. Now you go ahead and read the section in the text itself, do several problems related to that, even if they are not assigned. Make sure you're comfortable with these things so that later on you'll have easier time. Okay. Good luck and God bless, and see you in the next lecture.